Okay, hi everyone. My name is David Spickett. I work for ARM, but I'm assigned to Linaro, where I primarily work on LLDB. Disassembly, we all know it. We wouldn't use tools if they didn't have disassembly, because we'd be forever reading the manual, just a complete waste of time. So keep that in mind as I go through this example. I chose a branch of equal instruction, and the way that works on ARM is we don't have explicit operands to the instruction that we compare. We do an arithmetic instruction that sets a flag, which is a global entity, and then we later read that flag in the instruction. We can also read that out of a register if we're software, called the current program status register. So if you're in a debugger, you wanted to know if you were going to branch, you would print it out, but you get a hex value. So again, bad. Don't use LLDB. Well, I try to fix that. So turns out that GDB users have never had this problem. So in your average GDB session, you've got your debug server and your debug client. It'll send an XML document describing the debug target. That includes the architecture, the memory layout, memory types, the registers, and crucially, the contents of the register that are referred to as this flags element. And it's effectively the type of the register if you think of the register as a variable. And it describes these fields that have a name, a start bit, and an end bit. And then the debugger can use that to give you a nice display that looks like this. If a field is a single bit and is 0, it's not going to be shown. So because we can see the Z bit, that means that we would take that branch that I showed earlier. So I thought this was a great idea. I thought I'd steal it. Good news, we already use the target XML format for everything else that I mentioned. And LLDB has, as you've seen today in the Mojo talk and others, a long history of printing variables in fancy ways, however you want to print them. We don't parse that specific flags element, although how we do that is quite boring. I'm not going to cover that today. But the bigger bit is we cannot treat registers in this dynamic way. We can do vectors, but vectors are a subset of types. So I did that boring bit I just mentioned and wrote a bunch of new code to generate these tables doing bit shifts and masks to show the register. And this works fairly well. But as I said, new code, you have to extend it, you have to do everything yourself. So I decided to RFC it at this point. And the big key bit of feedback came from Jim Ingham, who suggested that we take this flags element and treat the register as if it was like a C struct as described by that flags element, and then reuse all that variable printing code that we already have to get all the existing features for free, but for registers. So this is how that works. You take your flags element, and for every field in that flags element, you make a field in your packed bit field struct, as you would see in C. LLDB doesn't need to actually generate C code because we link to Clang, so we can use its abstract syntax tree directly and make the equivalent of this structure. Then we're going to pretend that this is a variable in memory and print it out using the same infrastructure that we already use. And it turns out that this is not a new thing, it's just a subset of your build debug cycle. So starting at the top left, you've got C, you put that into Clang, you get an abstract syntax tree. Amongst many things you make, one of the things is debug information that goes into the object file. And then you have some bug you want to investigate, so you load that into LLDB. We then pull out the dwarf, and believe it or not, we make an abstract syntax tree to represent that dwarf, which is effectively a subset of that first tree. And then we can print that out in a nice way. So for registers, all we really need is those bottom right 2 boxes. So zooming in on that, LLDB server is going to send us some target XML that's got this flags element in it. We're going to receive that in LLDB, make a syntax tree, and print it. And the and print it bit is, we'll get on to next. So we want to make sure that regardless of what endian you're running LLDB on, this structure doesn't flip around. And we also want to match the architecture manual for whatever architecture you're using. In this case, for ARM64, the most significant bit is going to be on the left or the top of any diagram that you see. I mentioned we're using a packed bit field struct. If you were doing this in pure C, you'd have to deal with some implementation-defined behavior across compilers. The first one is you have this storage unit, which is some number of bytes. And if the next field you want to pack into that unit doesn't fit, you can either straddle the unit boundary, which will make it smaller, but maybe you need 2 accesses. Or you can push it into a new unit, makes it bigger, a single access for that field. We're going to sidestep that by saying each register is a storage unit. So we will pad to get the positions we want, and we know that we can't spill outside the storage unit by definition. The next one is, once you've put all the things into the units, what order do you have? Now, the compiler can't shuffle them arbitrarily, but it can effectively do top to bottom or bottom to top. Luckily, because we only link to Clang, Clang is the compiler, and it turns out that Clang's pre-cogen order is effectively big endian in the way that LLDB builds this type. So that means that that n field becomes bit 31, the most significant bit. So good news if you're using, well, we match the architecture manual as you want. So we have the most significant bit first, it'll end up on the left. If you're using a big endian target, or you're debugging a big endian target, great news, but most of you aren't doing that. Bad news, little endian values aren't going to work for those. But we can fix that by effectively taking our little endian register value and moving the fields around to fit the type. So we simply reverse the field order. We don't change the value of the fields, just the positions. And then the next bit is that registers don't traditionally have an endian. They just kind of exist as values in the CPU. So we've always stored them as host endian inside the debugger. And the last step of this is to pretend that the register value is a variable in memory. So we need to give it the endian it would have if it were in memory, if there's a mismatch between the host and target endian. You do all that, you put it through our existing infrastructure for printing types, and you get this nice output, a lot more verbose than GDB. Got the architecture manual at the bottom there for reference. There are some differences, but they are for usability reasons I won't get into. And if you want to answer our original question, we can zoom in a bit. We do our subtract, b.equal, we want to know if we're going to branch. We can see that z is 1, so we're going to take the branch. So the status of this is that the LLDB, call it the client, fully supports parsing information from any debug server that will send it flags. So that includes GDB server and a Game Boy Advance emulator, believe it or not. And if you want to use LLDB to LLDB server, that works fully on AH64 Linux and soon to be hopefully on AH64 FreeBSD. If you're looking at this thinking, I want this for x86, I want this for S390, it is a really good entry point for contributing to LLDB, because all we need you to add is the information about the registers, and I can help anybody do that if you want to do that, because I think, again, it's like disassembly. We should have it everywhere. It should be expected. People should complain when it's not there. And that's all I have. Thank you very much.